A car on a ramp is performing uniform circular motion along a horizontal circle shown as the dashed line in the figure below. The ramp has a banked angle theta and the circle has radius r. The car's mass is m. What is the speed of the car, velocity of the car, vc, that renders zero static friction between the tires and the ramp surface? So if we draw a free body diagram here, this is going to represent the ramp, and here is the block. So we have the normal force that's perpendicular to the ramp, and the force of gravity that's pointing directly down. There is no force of friction, since it says the speed of the car that renders zero static friction, so no friction is necessary to keep it moving in this circular motion. Now we can decompose this normal force into its horizontal and vertical components. The horizontal component is simply the normal force times the sine of theta, because theta is right here, and you can use basic trig for that. And then this component right here, the vertical component, is the normal force times the cosine of theta. And these are all the variables we'll need. So the vertical component of the normal force is going to balance out with gravity. Since it's performing uniform circular motion, it's not going to need any static friction to support it. And the horizontal component of the normal force is going to be the centripetal acceleration. It is what's going to be keeping the car moving in a circle. So this is simply equal to the centripetal force, which is the mass times the acceleration in the centripetal direction. So we can simplify this, saying that the horizontal component of the normal force is simply the mass times v squared over r, where vc is the velocity of the car. Now we can solve for the normal force using the first equation here. So we solve that the normal force is equal to the mass times the gravity divided by the cosine of theta. Now we can plug this back into the second equation. So we get that the mass times the gravity times the sine of theta, that is the normal force, divided by the cosine of theta. That's after you plug the normal force times that part, is equal to the mass times the velocity of the car squared divided by r. Now you can cancel out both the masses because you can divide both of them. And sine theta over cosine theta becomes tan theta. So you get that the gravity times tan theta is equal to the velocity of the car squared divided by r. Now you can simplify this even further to get that the velocity of the car squared is equal to force of gravity, or the acceleration due to gravity, times the radius times the tan of theta. Now I'm going to make some more space over here by erasing everything. Get rid of everything here. And then your final expression will be that the velocity of the car must be equal to the square root of the gravitational acceleration times the radius times the tan of theta. And this is the velocity that's needed. Any more than this, and you will require static friction to apply even more centripetal force so that the car won't go flying. And any less, and the normal force is going to provide a little too much centripetal acceleration, and the car will no longer be going in this circular motion. And that is how you would solve this problem here.